which is now the Quebec Oscar 100 satellite. And as you've heard on amateur radio today, there's already a lot of guys playing on the satellite. They've built their own things. Every guy so far that has put a system together is a slightly different design, but it's going to be very interesting to listen to Hannes and what he proposes. And actually to see a live demonstration of it working, which is absolutely great. Thanks, Hannes.
Okay, good morning. Oh, it's working there. Going to look at amateur radio's first geostationary satellite, the Qatar Oscar 100. Qatar is a bit of a strange word on the tongue for us, so we'll just use Oscar 100. I think it sounds much more natural the way it should be for us. So the presentation is I'm going to give a bit of a background on Oscar 100. We're going to look at the dynamics, what's the difference between a geostationary satellite and the low Earth orbit satellites that people are much more familiar with. Many more amateur satellites are low Earth orbit than what the geostationary ones are. The focus this morning is going to be specifically on the narrowband linear transponder, equipment that we're going to need, specifications of the transponder, frequencies that it's using, etc. I've built a ground station and sort of implementing my ideas, and then as you go along you learn a lot and you change your ideas and you look at on the internet and you see some other ideas. As more people get active on the satellite, you're going to get lots of different variations on the theme, which makes it very interesting. And at this stage most of the people are doing the homebrew thing, seeing that commercial equipment is not that common yet. So I'll present my possible solution and then the practical demonstration. At the moment the receiver is working very nicely, but Murphy struck a bit on the transmitter side. Live demonstrations are always a nightmare, so I do not see my downlink at the moment. I suspect that I've damaged my power amplifier with all the loose cables and things like that, but at least you can see all the building blocks. I've used it already to make some contacts into the Netherlands, France, etc. So it does work, but not just, only when there are not so many people around looking at you. So, okay, let's look at Ishal 2 to be more exact. The Qatar satellite company, which is known as Ishal now recently launched their second satellite, which is now Ishal 2. All these strange sounds on the tongue. They used the SpaceX Falcon 9 rocket, and the launch was on the 15th of November 2018. So then the SpaceX put the satellite in a geostationary transfer orbit, and then from there it was slowly maneuvered to what is now more or less its final position at this stage. Now the launch was supposed to have happened more than 3 years ago, in 2015, 2016 already, but being space orientated, everything slips, everything takes longer, and we're just glad that it eventually did happen after all these years. The negative part of it all is that a lot of people were very enthusiastic in the beginning, getting stuff together, and then for 3 years nothing happening, so the people lose their interest. Technology changes, things that were available, especially on 2.4 gigahertz, things have now moved up the Wi-Fi stuff to 5.8 gigahertz, so lots of the modules that were available then are now not available anymore. So you now have to look at the thing in a sort of bit of a fresh approach. To get the satellite into its final position took more than 2 months. It's then from November till I think it was actually early February where it was eventually parked at its final spot. It was parked a few degrees or it's fractions of a degree from where it was supposed to be. So everybody lined up their dishes, got a nice signal, and then they moved the satellite again. So it was also an interesting pastime, finding the satellite once again. So the main important thing is February was the time that the commissioning was completed. Also, the amateur transponder was the last module that was sort of commissioned on the satellite, because seeing that we're just hitching a ride, we're not contributing any turnover or any profit to the satellite, to the business. And then later in February, it was now made available for general use to the amateur community.
So the primary payload is TV?
Yeah, I'll say a bit more about that. So the important one here is the Qatar Amateur Radio Society that managed to secure the privilege to have an amateur radio payload on Ishul 2 on the DSTV satellite. So it saves us a lot of money, made a lot of things possible, because first of all, it is a geostationary satellite. It's very expensive to get the satellite up that high. And then it's a sort of a very, what shall we say, it's a hotspot, the geostationary orbit. They want to use it to make money. They don't want people to park their little amateur things in between where they can make millions and millions of dollars. So there's no way that we can easily do our own satellite and park it in one of these very highly preferred orbits as such. Okay. So then in February, when it was now finally commissioned, it became the Qatar Oscar 100, and the people just referring to it basically as Oscar 100. So it's actually a nice 100, the first geostationary satellite, goes nicely together. If we look a bit at geostationary orbit, what does it entail? First of all, it's a circular orbit, and it's only above the equator. Our low Earth satellites tend to be more polar orbits, sort of a north to south type of orbit. This is an east-west one, directly above the equator. The main, or the big secret, is that the orbital period is equal to the Earth's rotational period. So from the ground, it appears that the satellite is motionless. It's the same with your DSTV. Once you've put up your dish, it's always in the same spot. Low Earth orbit satellites, you have to track it, or some of these highly elliptical orbits, you have to track it all the time. This one is nice. Set it up, tune for maximum signal, and then nothing's going to change for a long while. So it can only happen at an altitude of 35,000 odd kilometers above mean sea level. Now that is quite a distance. Your typical low Earth orbit, once again 450 to 600 kilometers. The International Space Station, 450, 500 kilometers. So this is quite a distance. So your signal have to travel there and back. That makes for 70, 71,000 kilometers. So it's, you start to notice a time delay, among other things as well. If we look at our history, the high altitude amateur satellites, all the previous high altitude satellites were in highly elliptical orbits. That's to increase the area covered. With the low Earth orbit, you've got your footprint, which is basically, if it's about South Africa, it's about South Africa, your footprint. But you cannot work with the low Earth orbit. You will not be able to hear America or Europe or any of those DX countries. So with the previous high altitude satellites, they sort of used this technique to get to increase the footprint, that you can work some DX, not just your local country, and then also the availability, the amount of time that you can access a satellite. Problem with that is, of course, these orbits were sort of optimized for Europe, North America, the Northern Hemisphere. So it was very difficult for us here in South Africa to access those satellites. And, but you can understand the majority of the activity is in the Northern Hemisphere. And those satellites were known as Phase 3 satellites. And oops. Okay, we were looking at the history of Phase 3 satellites. Phase 3A being lost at launch, Phase 3B that became known as Oscar 10, that's still alive from time to time. If it hits the sun at the correct angle, etc., then Oscar 13, and then eventually the last Phase 3 was Oscar 40 that operated from 2000 to 2004. So it died a long time ago. And since then, there wasn't really any high altitude satellites for us. So your distances that you could work always very limited to typically the low Earth orbit applications. But now we're entering the new phase, Phase 4, with the geostationary satellites are going to start appearing, and then Oscar 100 being now Phase 4A. Now, as far as I know, the Americans are also working on geostationary satellites. So hopefully that will also happen within a couple of years, that it's now going to become much more common, not just this only satellite. If we look at from the satellite to the Earth, the antenna or amount of antenna gain that you can implement on the satellite is limited. If your 3 dB beamwidth is more than 17 degrees more or less, or if it's less than 17 degrees, you start to get spot beams. So you don't cover the whole footprint of the satellite. For commercial applications, that's quite acceptable. It doubles the capacity or increases the capacity of the satellite. But for us, we want the whole coverage. Everybody must be able to see the satellite. So that limits the gain on the satellite to about 20 dB. So whatever you still need in your link, you have to make up with your ground station, bigger antennas, more power, etc., as it's now limited on the satellite side of things. If we look at where Issel 2, the commercial satellite, is parked at 25.5 degrees. Since I did the presentation, it actually now moved to, I think, 25.8 degrees. So just to keep life interesting. But that's basically what you can see, the footprint from 35,000 kilometers up there. If you look at it from a different angle, it is huge. If you look at the left-hand side, you've got Brazil, and then of course all of Africa, all the way up to Russia, then Northern Europe, and then on the eastern side, it even hits some places like Vietnam. So that is a massive footprint. Everybody that will be able, or that are able to see the satellite. So if we translate that to some figures, that's basically a population of 5.2 billion people that are able to see the satellite, and they will, in other words, have access to the satellite. More important, it's nearly 1.5 million radio amateurs. So there is a lot of potential for lots of activity. It's more or less 225 DXCC entities that you're covering. I don't think we're going to see 100 countries being active for at least a year or so, because a big part of this footprint includes Africa, and the amount of amateurs are unfortunately declining in Africa all the time. So it will take some time, some of the expeditions to activate all of those countries. But there's lots of potential for the VHF, UHF people to get active there. Just repeating what we've said there, from Brazil, and there are actually stations just to the south of Sao Paulo that are active from Brazil at this stage. So it definitely is correct, they can work the satellite. Main thing here does not include mainland USA, for better or for worse. That's everybody's own personal opinion on that one. Okay. Now we look at the narrowband linear transponder. Although Qatar got the privilege, the opportunity to fly the transponder, they didn't have all the technical know-how, but fortunately our German colleagues stepped in. They did basically all the work. They did the design work, they did the prototypes, the commissioning, everything that goes with it. Even the ground station Dua were built by the German Amsat. Uplink is 2.4 gigs, and more or less a 250 kilohertz bandwidth. So eventually, when everybody gets active, there's 1.5 million radio amateurs. Fitting all of them into 250 kilohertz is going to be interesting, especially if you get your Italians and your Polish amateurs also among there, being very aggressive, very demanding. Well, I think work the satellite now while there's sort of not too much activity. On 2.4 gig, you require right-hand circular polarization. Although now that the satellite is on the air, lots of people are using linear polarization. You will see outside the station that I set up there, there's one of these Wi-Fi grids with the linear polarization, and lots of people are using it. It makes your life quite simple. You throw away about 3 dBs in your uplink by using linear polarization versus a circular, but mechanically it's much easier to do. And the 3 dBs you can make up with either a bigger grid or maybe running a little bit more power. So it's not a big issue. The downlink is in the X-band, or the 10 gigahertz, 3 centimeter amateur band, 10.489 gigahertz. So it's right at the top end of the amateur band. It uses vertical polarization, with us being here more or less right in line with the satellite. We're at about 28 degrees east, and the satellite being offset your feed like you have to do with the DSTV. That is now much more to the east. This one is due north, more or less due north from us. So it once again makes life much easier for us. Having only the 250 kilohertz bandwidth available means that the people prefer narrowband modulation techniques. SSB, CW, I've seen quite a bit of SSTV on there, so I expect in the future PSK 31, those type of modes are also going to appear quite a bit more. It was designed that you can use about 5 watt uplink power and then 60 to 75 centimeter offset dish. Technology's been changing. You now don't get 60 centimeter dishes anymore. 3 years ago you could get them, but since they moved to the high definition TV, 80 centimeters is now sort of the minimum size. So they are quite cheap. It's what I've got set up there as well. And yeah, some people have used as little as 7 milliwatts on CW to work through the satellite. But of course, if you don't know the signal is there, you're never going to hear it. You have to, on your downlink, use very narrow filters to actually hear the beacon signal. I've managed to hear my own signal with something like 40 or 50 milliwatts. Then I get the 3 dB signal to noise ratio. Typically for SSB, you want about a 12 dB minimum signal to noise ratio for a comfortable conversation. Lots of people that I've measured, they run up to 30 dB signal to noise, so it's nearly hi-fi. It's a bit overdone. I think the average is about a 20 dB signal to noise that you will find at the satellite at the moment. So it's nice, it's armchair type of copy, the signals. At this stage, I haven't seen it in operation yet, but there's Layla 2, quite an angry lady that's been implemented on the satellite. That Leistungslimit-Anzeige, the input power limiter, is to ensure fair play. In other words, your California kilowatters or your Polish megawatters, that they don't hog the satellite. The moment your uplink signal is too strong, automatic gain control of the satellite is going to kick in and it's going to push all the other people into the noise. And that's not what you want to happen. So they monitor the spectrum all the time, and the moment that the signal is above the threshold on your downlink, they start sending beeps. And as far as I understand it, they're also going to notch your signal so that you don't overdrive the satellite. So it gives everybody a fair chance. So the DXers that cannot work any station unless they've got the kilowatt and the biggest antennas, this is a different playing field. You're going to need a bit of more technique to achieve your DXCC eventually. So once again, the 5 watts or 1 watt, or whatever the case may be, it's just a couple of dB, 6 or 7 or 8 dB difference between 1 watt and 5 watt. It's going to be good enough. You're not going to need this massive power amplifier to work the satellite. So if we look at the uplink possible solution, it's a solution that I've implemented. Start with a 2-meter rig, lots of 2-meter rigs available, IC706, the all-mode rigs. I've got the older Yaesu there, FT221R. So 10 watts is a very common driving power or output power. So that's typically what you're going to sort of use as your signal source. And then the approach is going to be sort of for the lazy people, as easy as possible. Not in the olden days, we've got all these multipliers and filters and amplifiers, and unless you've got access to a very good lab, you cannot get the signal at 2.4 gig. So the modern approach is as simple as possible, using water-out components. So the block diagram of what I'm using, you start at the left with your 2-meter transmitter. 10 watts is too much to put into a transverter, so you need an attenuator to get that down to about 1 milliwatt. Between 1 and 5 milliwatts, you've got your mixer. And then for the local oscillator, the analog devices, PLL evaluation board is a very nice option. It covers, or it goes up to 4.4 gigahertz, so 2.4 gigahertz, no problem for it. Arduino to control it, set it up to the correct frequency, and there's your LO sorted. It's not like it used to be in the old days, crystal oscillator, multiplier, all that type of things. Need to filter your correct component, amplify it, filter some more, get rid of all the junk, and then eventually you end up with your power amplifier being 1 watt or 5 watt, something in that vicinity is good enough. So it's quite a simple block diagram. I've also, the little exhibition we've got there at the back, I've put 1 or 2 of the up converters there, but you can see how this was implemented. The phase lock loop and the Arduino controller is outside by the station. Power amplifier, this is the one that I'm using, 5 watts at 2.4 gigahertz. Power gain of 17 dB, that means you need to feed it about 100 milliwatts to get to the 5 watt level. And it is linear, because for SSB you need the linear amplifier. So it was now meant for Wi-Fi, OFSK, all those modulation techniques. So that actually works very well on SSB as well. I was a bit worried that it was going to distort the signal, but not a problem there. This is my implementation of the phase lock loop, or the VFO. Just the LCD on the left showing your frequency, and then here on the right you've got the output that goes into the mixer. This one uses a PIC, but the one with the Arduino is actually much easier to build and much easier to get going. The one that I recommend that you can look at with the Arduino is by Fox6KBF. You can find that on the internet, just a quick Google search. And his code, the sketch, the Arduino sketch is available. Just load it into your Arduino with the shield there, LCD shield, and it's as simple as that, I2C. On the right hand side is the Arduino, the ADF evaluation board, and there's your 2.4 gigahertz LO sorted. No crystal oscillators, multiplier change, and all of those interesting things. Another look at the evaluation board. If you now buy it via eBay or AliExpress or Banggood, it's more or less $20, including shipping, so it's not a lot of money. And you just feed it 12 volts on the one side, I2C control on the other side from the Arduino, and there you are, simple as that. There are, of course, other options as well. The more modern ones that now became available is the SDR approach. So it can either be a hack RF, or it can be a line. Any of these SDR transmitters. Most of them goes up to about 6 gig, the modern ones. So it's no problem covering 2.4 gigs. So you'd use your laptop, your microphone for your laptop, controls the SDR transmitter, and the output you just feed into the amplifier. And even simpler than the other approach, there's your whole transmitter chain sorted for you. If we look at to receive the signal, in the olden days, 10.4 gig equipment used to be quite complicated, expensive, and everything that's nasty. But technology have changed. So what we found that's working very well is the normal, like a DSTV, the LNB, low noise block, the LNB down converter. It's very affordable. The one that we've now found that works very well, you can get one for about 160 or 170 Rand. So it's not a lot of money, but you get a lot of technology for that little amount of money. So on these KU-band DSTVs, just running it off 12 volts, select the 9.75 gigahertz allo, which is very convenient for us. In other words, you just use your normal shack power supply. No need for 18 volt and fancy power supplies. What you've already got in the shack will most probably work 100%. So if you take your 10.489 gigahertz, you subtract 9.75 gigahertz from that, your component is at 739 megahertz, more or less. Now 739 megahertz is quite a distance from any of our amateur frequencies. We've got 430 megahertz and we've got 1.2 gigs, but nothing in between. So in the olden days that would have been a problem. You would have had to build your own receiver or another down converter. But fortunately, that's also long gone. With the RTL SDR solutions, they actually optimum at that 739 megahertz band, because it's in the TV band, and these RTL dongles were designed to receive TV signals. So you're now feeding it something that it actually wants to see, and it works very well. So at the end of the day, you use one of these RTL dongles and then an SDR solution on your laptop. Now there are quite a few of those SDR solutions available. It's SDR Sharp or HD SDR or whichever one you prefer. But very easy, and you get all these nice benefits. Click the tune and you get waterfall display, everything that goes with it. So the receiver chain that I've got running there at the back, I've got the 80 centimeter dish, the KU-band LNB, the bias T just to inject the DC for the LNB, your dongle. It can be RTL dongle, it can be a more advanced like a FunCube dongle, or it can be a Lime receiver. Any one of those will do the trick. Goes into your computer, laptop via USB, and then you've got your software application, and there's your whole receiver chain. Simple as that. And it works, actually, it's very nice, very convenient. Okay. Just to have a look at the block diagram of the LNB, the ones that you now buy for 170, 200 odd Rand. Feed on to the left, you've got your low noise amps, vertical or horizontal polarization that you can choose. But feeding it 12 volts automatically selects vertical polarization, and it selects a 9.75 gigahertz allo. So you don't have to feed it any control signals. Feed it your 12 volts or 13.8 volts, and there you've got your solution already tuned, set to the correct modes. To get DC into it, you're going to need a bias T or a DC injector. Once again, very simple. I've got examples there at the back that you can have a look at. Inductor that you just wind on a 3mm drill bit, DC blocking capacitor, and then the diode there at the bottom. It's what they call the idiot diode, in case you put the reverse polarity to your LNB, that you don't pop it. So it's simple as that to get your LNB up and running. Options for suitable LNBs. You've got here the Avenger. This is available from Europe. It's quite a pain with our post office to get hold of them, and they work out 400 odd rand at least, sometimes a bit more. But that, if you've got people in Europe or visiting Europe, that's the one to look at. The other option is the Octagon. The German people prefer this one. If you read on the internet, they all use the Octagon in Germany. So quite a nice high stability LNB as well. But don't believe everything that you read. It says the noise figure 0.1 dB. Now that is typical Chinese specifications. I think the in reality noise figure is probably between 0.5 and 1 dB. Definitely not 0.1. That's a bit optimistic. And then the one that's locally available that I'm using as well is this Amsat LNBU 10.6. Those are now two boxes on top of each other, the one side and then the back side of the box, actually specifying phase, noise and stability, all those actually sort of more professional type of specs. So it tells you it is quite a quality product, and for the amount of money that you pay for it, you definitely can't go wrong. So they used to be available at Dominica, but they now sold out. But Builders Warehouse or Chamberlain's, they also stock them from time to time. And so just look for the correct one, that you get the high stability option. If we look at the receiver side, low cost RTL dongles, what they look like. The dishes that I use, once again, also DSTV dishes. On the left hand side is the receiver. Right hand side I've got the helical feed for the uplink. So left is 10.4 gig, right is 2.4 gigahertz. Uplink, downlink. No problem with interaction between the two. It's not, my transmitter is not interfering with the LNB. It's not popping the LNB, anything like that. I think in the future we're going to see that you've got two feeds onto one dish. They're going to 3D print a nice adapter. You've got your 10.4 gig LNB and then put your helix next to it or somewhere in the vicinity that you use the same dish, which will make it even more convenient. Because if you align it on the receive side, then automatically the transmit side is also working correctly. I've heard some people using a dual feed already on the air, and it's not that they popping the LNB, the gas fed in the input or anything like that. So I think that's going to be more popular in the future. The SDR Sharp, the software application that I was using here, shows you at the top the spectrum where you can see the signals, and then at the bottom is your waterfall. That's a history or sonogram of the activity. Makes it quite easy to find your own signal. When you do look at the satellite, you will see all these carriers sweeping around. Because what the people do to find themselves, if the station comes up, they click on it to listen. Very easy on the receive side, but now you need to get your transmitter on the same frequency. So they just key the transmitter and tune and see until your signal is on top of the other person. So it's a bit antisocial, but it's very effective at this stage when there are not other people on the air. On the right-hand side, the satellite, the transponder was actually very well thought out. On the right-hand side, you can see the two peaks there. That's the upper beacon. So that's the highest frequency of the 250 kilohertz. Now those two peaks are PSK 400 signal. Oscar 40 also used the same format, the PSK 40 or PSK 400. You do get software that can decode it for you, so the telemetry is in there, things like the voltages, temperatures, that type of thing. But it's a very nice beacon because it's always on the air, and with the PSK your amplitude stays more or less constant. So when you set up your station, tune it to the upper limit, you get your SDR, your app running, and it's as simple as turning your dish maximum signal on the receive side, on the upper beacon. Makes it very easy to find the satellite and to optimize your alignment. On the left-hand side, right at the left, you can see there's also a signal. That's a lower beacon. Now that's a Morse code beacon that they use. Also identifying the satellite, and then it's got the time period where it's a constant carrier, just like the Northern California DX Foundation, those beacons at this constant signal level. So you can very quickly see the bottom of the spectrum and the top part of the spectrum, and then the other signals. If we look there at the left, there's SSB signal. Everybody's using upper sideband on the satellite, and you can see on the sonogram the waterfall, the activity. Click on it and you can listen to the conversation. Of course, with the technology advancing, there are other options as well available, and that's the web SDRs. You don't physically need a receiver, you just need access to the internet, and you can start to listen to the activity. So this one is Anton's web SDR, where once again at the bottom you've got the waterfall. You see there at the right hand side there's a PSK beacon, upper limit, and then once again also some SSB activity there to the left. Simply click on it and you can listen to whatever's happening. So that is, in short, the bit of a background about our latest satellite, a new dawn for us with the geostationary satellites, the Oscar 100. Just turn the laptop a little bit that people can see, then I can demonstrate, or if people are interested, they can have a look there, maybe during lunchtime or so. I can show you the beacon, and you can listen to some of the voice transmissions, etc. there on the laptop. What makes it also quite nice, if you use the same dish for the transmit and the receive side, you just take your feed from the one and put it on the other one and align it. Then your transmitting dish and your receiving dish are then properly aligned. Otherwise, with the transmitter, you have to look at your downlink and then adjust the dish and to see when you've got maximum signal. But there's a bit of a delay with the 70,000 kilometers, so you tend to miss that optimum point because you see the peak of the signal too late. So it's easiest just to use or to move the LNB between the two dishes. Yeah, and as always, it's all about having fun and being active. Get on the satellite, start playing. To receive is very easy, very cheap, and it's quite an experience. You learn a lot in the process. Any questions? Any?
Can you say the version again?
Okay, when you do set up your dish, here from us it's about 60 degrees, 59 point something. The modern dishes at the side, they've got the elevation angle that you can just tilt it till you get the 60 degrees. The old dishes only went up to 50 degrees elevation angle. So you had to file out and measure and things like that. But if you buy yourself a new dish, look at the side, set it to 60 degrees, and then you sort it. Then you just need to do your direction, because you don't have to do the elevation and direction at the same time. That gets a bit hairy. So it's very simple. Set your elevation and then just look for the satellite. Being at 25.8 degrees east, it works out to about 4 or 5 degrees to the north. In other words, 356 degrees. So if you get north, just a little bit to the north is where you'll find the satellite. And the beam width, you're probably looking at about 10 degrees. So it's 5 degrees either way. So it is a bit sensitive, but it's not that critical. It's relatively easy to do the alignment.
Do you know whether this signal strength indoors will be adequate for a dish like that? I'm thinking of people like myself, who live in a complex. You can't put up a dish outside.
Yeah, what we've seen and what I've heard, what Frick has also done, is just using the LNB. No dish, nothing. And if you know where to point it and you look at the spectrum, you actually start receiving signals. So if you use a small camping dish, 30 centimeters or something like that, or even this one, 80 centimeters indoor, through a window, north-facing window, you should actually work quite well. Yeah, the loss through glass at 10 gigs is not that much. So it should be, even for people living in complexes, you're not allowed to put up any antennas. It will also be very accessible.
But you can put up a satellite DSTV dish.
Yeah, but lots of these complexes, they've got a central dish and they just feed it to everybody, so they don't like you to put another one on. Yeah, lots of people also now do it via the internet, so the moment you now even put the DSTV dish on, they start knocking at your door. But you can hide it easily.
I've heard some German guys who've just a portable dish, he just puts it next to his window, he's booming the satellite, and he's finished, he just goes and puts it.
Yeah, put it back into the house. It's so easy to align.
I think they've got much lower elevations, and you just need to worry about it because it's quite high for us.
Yeah, the 60 degrees is, if there are double-story buildings, things like that in your way, just make sure that you clear it. Yes.
Does the satellite also have a wideband transponder on it?
Yes, there is a wideband transponder. A little bit higher up in frequency, a bandwidth of 5 megahertz, if I remember correctly. It's intended for digital satellite TV. But I think to receive it is going to be quite easy. You're using the same dongle, same setup, different software, but you have to select horizontal polarization. So either you need the control signal or you simply just tilt your LNB if you want to look at that. On the transmitting side, uplink is also 2.4 gig, just a little bit up, but you're looking at about 100 watts to get into that transponder. So once I've sorted out the narrowband transponder, everything working nicely, it's going to be the next challenge to try and see what it takes, what easily available sort of cheap equipment you can get to work the wideband transponder. So come back next year, maybe we've got some info for you then. Good. Okay, any other questions? Thanks.